Picture this for a second. You're zooming from Los Angeles to San Francisco, and it takes you exactly 30 minutes. You're just chilling in a pressurized pod inside a vacuum-sealed tube, blasting along at over 700 miles per hour. No traffic, no weather delays, literally zero friction. Now, this was the captivating promise of the Hyperloop, right? The so-called fifth mode of transport that was supposed to completely upend human travel. Look, we've all seen the gorgeous renders, the sleek pods, and honestly, it's hard not to get swept up in the hype. But in this explainer, we're going to pump the brakes a bit and unpack the harsh, frankly unforgiving engineering realities hiding right beneath the surface of this breathtaking vision. Because that immediately forces us to ask, how do we actually build this thing? It is incredibly easy to spin up some sleek 3D animations. But reality? Reality is a completely different beast. We're stepping into the brutal world of hardware startups here. You see, unlike software where you can just move fast, hack something together in a garage and iterate, hardware demands raw materials, it requires massive factories, and extremely heavy regulation. You literally cannot code a 500-mile steel tube into existence. So to figure out if this is an actual revolution or just a multi-billion-dollar pipe dream, we have to strip away the marketing and look at the terrifying physical demands of actually building this system. Let's jump into Section 1, the dream and the catch. To peel back the very first layer of this engineering onion, we need to look at the foundational physics of high-speed tube travel. The absolute first massive hurdle you hit is something engineers call the piston effect. Take Japan's maglev trains, right? Unbelievable feats of engineering, but they face this exact issue. When a train blasts through a tunnel at high speeds, the air sitting in front of it has nowhere to go. So the vehicle basically acts exactly like a plunger inside a syringe, compressing all that trapped air and creating immense aerodynamic drag. And the crazy part? The faster you try to go, the harder that air pushes back. The energy required just to shove the train forward shoots up astronomically. So, to get around this, the Hyperloop pitches a theoretical magic bullet. Just remove the air completely. The idea is, if you create a near-perfect vacuum inside the tube, you literally eliminate the drag. And in theory, it's a beautiful, elegant solution. It would let you hit Mach 1 speeds with barely any energy input at all. Sounds flawless on a whiteboard, doesn't it? But here's the kicker. Pulling a vacuum inside a controlled laboratory is one thing. Doing it out in the wild is a totally different nightmare. Which brings us to Section 2, the physics of the tube. Now we have to confront the monumental material science challenge of maintaining a hermetic seal the size of an entire state. To really wrap your head around the sheer scale of this problem, think about the famous Kola super deep borehole. It took teams of engineers 2 agonizing decades to drill a hole just 12 kilometers deep. 2 decades! Now take that immense level of effort and try to imagine building a structure spanning, say, 500 miles across an American state. And you have to guarantee that every single inch of that massive structure remains perfectly, hermetically sealed against the outside atmosphere. It's mind-blowing. But actually, your biggest enemy isn't even creating the vacuum. It's thermodynamics. Let's look at the moon for a second. Up there, temperatures can swing by nearly 300 degrees Celsius, which causes materials to violently expand and contract. Now, obviously, Earth isn't quite that extreme, but the localized heating effects on a massive, miles-long metal structure present a devastating threat. We're talking about thermal expansion. Just picture a 500-mile-long steel tube sitting right out in the open, baking under the hot California desert sun. As that metal heats up during the day and then cools off at night, it naturally expands and contracts. Across hundreds of miles, that physical expansion compounds. That steel tube will literally contort and shift by the length of several football fields every single day. It's basically like a giant metal worm just crawling its way through the desert. Now, engineers have definitely battled massive thermal expansion before. Look at the legendary SR-71 Blackbird. They solved it by literally designing leaky titanium joints. The plane's skin actually leaked fuel while it was just sitting on the runway. But once it took off and hit supersonic speeds, the intense friction heated the titanium up, caused to expand, and sealed those gaps perfectly. It's genius. But here is the massive catch. You absolutely cannot use leaky joints on a vacuum tube. The literal second you introduce a gap to give the metal room to grow, you lose your vacuum. Game over. And what happens if that seal fails? Say even a tiny crack forms because of that structural flex. Well, the atmosphere doesn't just gently leak back into the tube. Because the pressure difference is so extreme, the outside air violently rushes in at supersonic speeds. We are talking about a literal, solid wall of air tearing straight down the tube, and it would completely obliterate any oncoming pod traveling at 700 miles per hour. It's a terrifying scenario. All right, Section 3, trapped at Mach 1. Let's shift from the tube itself and look at the incredibly unforgiving aerodynamics of the pod. Once you're inside that tube, the physics gets incredibly dicey. You have to perfectly balance the pod's center of pressure against its center of gravity. Remember, you're rocketing along at 700 miles per hour. At that speed, even a microscopic imperfection in the track, or maybe just a slight shift in where the passengers are sitting, can create what aerodynamicists call a capsizing moment. And unlike a normal airplane that has the whole open sky to maneuver and self-correct, this pod is trapped inside a steel cage with only centimeters of clearance on every side. There is zero room for error. Because of those tight margins, you're essentially flying an inherently unstable airframe. To keep that pod dead centered at Mach 1, you would have to rely completely on automated software overrides, making microscopic adjustments thousands of times a second. And we've all seen exactly what happens when you use software to constantly patch over an unstable physical design. Just look at the tragic case of the Boeing 737 MAX. It introduces this massive systemic risk where, if the automated systems fail, they fail catastrophically. Human reflexes simply cannot react fast enough to save the vehicle. You know, moving fast and breaking stuff is a fantastic motto if you're building a photo-sharing app. But out here, in extreme environments where failure is literally a cliff edge, it is an absolute recipe for disaster. We saw this exact horrific danger play out with the OceanGate submersible tragedy. When you apply lax engineering principles and disregard the harsh realities of physics in an environment that is completely hostile to human life, your margin for error is exactly zero. So think about what happens when things go wrong. Walk through this agonizing emergency scenario with me. Let's say a pod loses power and gets stranded. You can't just pop the door open and walk out into a vacuum. First, the system has to repressurize that massive section of the tube. And depending on the pump rates, which, by the way, is a logistical nightmare akin to the rapid detanking issues we've seen with Firefly's Alpha rocket, that repressurization could take multiple minutes, maybe even hours. If there's a fire or a medical emergency inside that pod, those agonizing minutes are quite literally the difference between life and death. Moving on to Section 4, the unforgiving economics. Let's zoom out and ask, is this system even remotely financially viable? At the end of the day, engineering is always a brutal battle against the levelized cost. Now, traditional high-speed rail is already incredibly expensive, but maglev systems, they are currently sitting at around 11 times more expensive per kilometer than traditional rail. Just look at Japan's Tokyo to Nagoya maglev line. It's projected to cost well over $13 billion. Why? Largely because 86% of it has to be buried underground just to handle the intense physics of high-speed travel. And then we arrive at the Hyperloop. Here, the cost factor isn't just high, it's practically astronomical. And the reason it's astronomical is that a Hyperloop startup isn't just building a faster train. They are being forced to simultaneously perfect 3 distinct, wildly expensive engineering realities at the exact same time. They need the pinpoint track precision of a maglev, wrapped inside the immense scale of a space-grade vacuum chamber, all while housing passenger pods that have to be built to the structural standards of a deep-sea pressure vessel. Fusing those 3 things together is mind-bendingly expensive. So, what's the ultimate takeaway here? It's a stark, undeniable warning. You absolutely must respect the unforgiving laws of physics. When massive, multi-billion-dollar giants like Boeing try to skirt around careful certification to save a few bucks, we've seen it end in tragedy. For any hardware startup out there attempting to build the Hyperloop, they are going to need way more than just venture capital and pretty PR renders. They need an absolute, unwavering respect for the physical limitations of our world. As it stands right now, the Hyperloop basically functions as a technological Frankenstein. It is genuinely a brilliant, fascinating concept, but it's one that is likely far too complex for where our current material science and economic realities are today. But look, I want to be super clear. That doesn't mean we should just stop pushing the envelope. Think back to the P-38 Lightning during World War II. That plane was considered an absolute monster when it was first assembled. But because its visionary designers understood the physics, they knew how to be quick, quiet, and reliable, it revolutionized aviation. The Hyperloop, it's simply our modern boundary-pushing monster. And that brings us to Section 5, system logic and mastering the physics. Because really understanding how these massive systems behave means you have to grasp the rules that govern them. Now, if you're as fascinated by these crazy concepts as I am, and you actually want to grasp the applied physics and classical mechanics behind them, you absolutely need to check out Brilliant. What I love about them is they don't just force you to sit there and memorize dry textbook formulas. Instead, they use these amazing interactive hands-on lessons that let you literally see the physics in action. Whether you're visualizing how ions flow in a battery or figuring out exactly how logic gates physically build a computer, it just clicks. It really is an incredible way to learn. So if you want to level up your own engineering toolkit and really understand the world around you, head over to brilliant.org/systemlogic, or just click the link down in the description. And hey, by using that link, the first 500 of you are going to get 20% off an annual premium subscription to Brilliant. It's a fantastic resource. Definitely check it out. All right, that leaves us with one final provocative question to chew on. If we absolutely cannot cheat the unforgiving laws of physics, what boundary-pushing engineering marvel are we gonna attempt to build next? Thank you so much for joining me for this explainer. Keep asking the big questions, and I'll catch you in the next one.